Welcome viewers. In this video we will see the magnetic circuit and basic definition of the magnetic circuit. First we will see the magnetic circuit. Consider this is the core is available, iron core is available, over which the coil is winded with n number of turns. The coil is winded on one side, n number of turns are available. When the coil is energized with the voltage, the current is flowing through the coil. Due to rate of change of flux, due to rate of change of current, flux is produced in the coil. So that flux is following this closed path. This following through the core. The core is now, this is the square shape, mean the flux also following in a square form. That is A, B, C, D, A. It is following the path A, B, C, D, A. So this closed path is nothing but a magnetic circuit. This is the flux, the closed path is nothing but a magnetic circuit. So we have iron core is available, over which coil is winded. When the coil is given with the supply, current is flowing. Due to rate of change of current, flux is produced in the coil. That flux is follow the closed path A, B, C, D, A through the iron core. This closed path A, B, C, D, A is nothing but a magnetic circuit. So that is given here. Consider a coil, n number of turns, winded on the iron core as shown in the diagram. When current is passing through the coil, magnetic flux is produced in the coil. The flux follows the closed path A, B, C, D, A. Hence, the A, B, C, D, A is nothing but a magnetic circuit. We will see some more details in that. The moment of charge carriers constitute the current. When the voltage is given, due to the charge, due to the movement of the charge, the current is flowing. The current flows in the conductor if it forms the closed path. When a current flows in a conductor, it will produce the own flux. The closed path followed by the magnetic flux is called a magnetic circuit. That is A, B, C, D, A. In a magnetic circuit, the magnetic flux of lines leaves from north pole and pass through the entire circuit and return to the starting point. Right? It is a closed path. Magnetic circuit also a closed path. It leaves from the north pole. A magnetic circuit usually consists of magnetic material having high permeability, such as iron, soft steel, because these material offer very small opposition to the flow of magnetic flux. Right? So the magnetic material with high permeabilities are normally used, such as iron or soft steel, because it offer the very small opposition to the flow of magnetic flux. So this is nothing but a magnetic circuit. Now we will go to the definition. The definition of magnetic quantities. The first one is magnetic flux. The symbol is pi. So the magnetic flux is nothing but the magnetic lines of force produced by a magnet is called a magnetic flux. So the dotted line available in the diagram is nothing but a magnetic flux. We assume that the flux is flowing through the core, that is the A, B, C, D, A. Right? So the magnetic lines of force produced by the magnet is nothing but a magnetic flux. The symbol is pi. The unit is Weber. Then magnetic flux density. Density means it is divided by area. Right? So the magnetic flux density is the flux per unit area at right angle to the flux. The density normally refer either area, length or volume. Here we are referring with the volume. So what is the flux available for a given area is nothing but flux density. The symbol is B. So the unit is Weber per meter square, because pi by A is there. So Weber per meter square. This magnetic flux should be at right angle to the flux. Then we will go to the magnetomotive force, MMF. Magnetomotive force, MMF. So what is the MMF? It is the cause for producing the flux in the magnetic circuit. So this is the source for producing the magnetic flux in the magnetic circuit, magnetomotive force. So this is nothing but obtained as a product of current flowing through the coil and n number of turns. MMF equal to n into I. Right? So the MMF is the cause producing for flux. It is a source for producing flux in a magnetic circuit. It is given by number of turns into current. how many turns available and what is the current flowing. These two parameters will determine the magnetomotive force. So the unit is N into I means ampere turns. I is ampere, N is turns, ampere turns. Then we'll go to the magnetic field intensity or magnetizing force. Intensity, again we have intensity is there. So already we discussed density, here intensity. It is defined as mmf per unit length. Here we are dividing by length of the magnetic flux path. Right. So the magnetic field intensity is nothing but mmf per unit length of the magnetic flux path, that is Ni divided by L. What is the magnetomotive force for a given length? So there ampere turns per meter is the unit, the symbol is H. So it will determine what is the magnetomotive force available for a given length, so that it is a measure of ability of the magnetizing body to produce magnetic induction in other magnetic substance. So it will measure the ability of the magnetizing body. How this magnetic circuit will produce the flux in the flux linkage with the other magnetic substance. So this is intensity. What is the intensity? How far they said has the intensity to link with the other magnetizing substance, that is given by magnetic field intensity or magnetizing force. Next one is the reluctance. So it is the opposition that the magnetic circuit offer for a flow of magnetic flux. So it is very similar to resistance. Resistance will oppose the flow of current. So this reluctance is oppose the flow of flux. So this reluctance is very similar to resistance in the electric circuit. So it is given by, it is a ratio of mmf to the flux, Ni divided by pi, mmf divided by flux. So the symbol is S. The formula is Ni divided by pi, right. So the reluctance means it is very similar to resistance. It offers the flow of magnetic flux. It will oppose the flow of magnetic flux. It is given by Ni divided by pi. Then we will go to the permeance. So permeance is the reciprocal of reluctance. That is, it is the readiness which magnetic flux is developed. It is reciprocal. Reluctance means it will oppose the flow of flux, but this permeance means reciprocal, so that readiness, it is the source for producing the magnetic flux. It will allow the magnetic circuit to produce the magnetic flux. So the permeance equal to 1 divided by reluctance. Then we will go to the one more parameter, permeability. It is a measure of the resistance of a material against the formation of the magnetic field. So this is one of the parameter that will determine the resistance of a magnetic material in order to form the magnetic field. In simple words, the permeability of the material means conductivity for magnetic flux. Conductivity, it will determine what about the resistance available, what is the conductivity of that material. It will determine this parameter. So we can obtain from this the magnetic flux density B is proportional to the magnetizing force. B is directly proportional to H. The magnetic flux intensity is directly proportional to magnetic field intensity. So while equating, we introduce this constant permeability, B equal to mu H. This permeability, this constant is introduced while equating this equation, B equal to mu H. So that it will determine what is the resistance or what is the conductivity of a material. So from this above equation we can write mu equal to B divided by H. Mu can be calculated from formula B divided by H. That mu is having two terms are available. Mu equal to mu naught into mu r. Mu naught means absolute permeability. Mu r means relative permeability. Now we will see what is meant by absolute permeability and what is meant by relative permeability. The absolute permeability of a vacuum or free space. Absolute means it is a free space, it is a constant, 4 pi into 10 to the power minus 7. So the absolute means it is a vacuum, it refers the vacuum or free space, that value is constant, 4 pi into 10 to the power minus 7. Now we will go to the relative permeability. Relative permeability of a medium or material is defined as the ratio of flux density produced in that medium or material to flux density produced in vacuum by the same magnetizing force. So it is depends upon the medium or material. So we are measuring what is the magnetic flux density in that medium divided by magnetic flux density in a vacuum for a same magnetizing force. So we are measuring the ability of that medium with reference to the vacuum. So this will be differ for a material. This is given by the manufacturer. For iron, steel means the constant value will be there. So it will measure the ratio of flux density of that medium or material with respect to the vacuum while passing the same magnetizing force. So in this video we discuss about the what is magnetic circuit, what is a magnetic path, and basic definition of the magnetic circuit. Thank you. Welcome viewers. In this video we will see the analysis of the magnetic circuit. There are three different types of magnetic circuit available. One is simple magnetic circuit, series magnetic circuit, and parallel magnetic circuit. First we will see the simple magnetic circuit. It is having only single core, single type of core, so that it is called a simple magnetic circuit. Let us consider a circular solenoid or toroid coil having a magnetic path of L meters. The area of cross section A meter square, and a coil have n number of turns carrying a current of I ampere. So that is given in this diagram. So this is called a toroid. The circular form means toroid or circular solenoid. Solenoid means normally the linear form. If it is solenoid is bent in the circular form, this is called a toroid. Here we have n number of coils are available, number of coils n. The current is flowing through this coil I. Due to rate of change of current, the flux is produced that is following this circular path. This dotted line is nothing but a flux. Due to circular core, the flux is also following the circular path. So this is the core. So this radius is nothing but mean radius of the core, because it is measured at the center, so that is called a mean radius. If it is internal mean internal radius, outside means external radius, but here we are measured at the center, so it is a mean radius. Now we will analyze this circuit. So according to the definition of the magnetic field intensity, H equal to Ni divided by L. Magnetic field intensity is nothing but mmf per unit length. This length is nothing but 2 pi Rm. That is, the length is nothing but circumference of this core, because both are equal. Length is nothing but a circumference. Circumference means 2 pi Rm. Rm is the mean radius. From that we can find the magnetic field flux density B. B equal to mu naught mu r H. The relation is available. B equal to mu H. That is mu naught mu r into H. Now substitute this H from the above equation. So that mu naught mu r into Ni divided by 2 pi Rm. Again this 2 pi Rm is written as L. So what we got, B equal to mu naught mu r Ni divided by L. Magnetic flux density is nothing but mu naught mu r Ni divided by L. These are all very basic formulas. From basic formula only we got this value. The magnetic field intensity also given in another form, pi by A. This is a normal definition. Magnetic field intensity is nothing but magnetic flux density is nothing but magnetic flux per unit area. So cross multiply this, so that pi equal to B into A. So B already we calculated. One formula is available. We substitute here. So mu naught mu r Ni divided by L into A. So we got the expression for pi by multiplying B into A. B is already available here, that is substituted. We got this value. Now we will go for further simplification. So that pi equal to Ni divided by L into mu naught mu r into A. So this mu naught mu r available in the numerator, now it is brought into the denominator. So that 1 divided by, so that the originality will not change. So L divided by mu naught mu r means while going to numerator it will be as it is. So this L divided by mu naught mu r A is nothing but a reluctance. We have one term resistivity rho. Rho equal to R equal to rho L by A. Like that we have L by A is there. The rho is now replaced by mu naught mu r. So L divided by mu naught mu r A can be written as a reluctance. So this term can be replaced by S, right? L divided by mu naught mu r into A. So that flux pi equal to Ni divided by S. From that we can write the reluctance. Reluctance, yes, bring this, interchange these two terms. So S equal to Ni divided by pi. So this is a simple magnetic circuit. By substituting the values one by one, finally we got the reluctance S equal to Ni divided by pi. The basic formula for the reluctance. Now we'll go to the series magnetic circuit. Series magnetic or composite magnetic circuit. What is composite magnetic circuit? It consists of three different magnetic materials. In the previous derivation we have only one magnetic material, but here three different magnetic materials available. These three different magnetic having the different value of relative permeabilities, along with the air gap also available. So three different magnetic material with three different relative permeability along with a air gap is available. It can be interpreted from the diagram that flux lines find the closed path through the different magnetic material and air gap. But the flux is flowing through all these three different magnetic material and the air gap, but only one flux is available. Thus a single significant magnetic flux is exist. So that it is called as a series magnetic circuit. Even though there is a three different magnetic material, but the flux lines are flowing in a single magnetic flux is exists. So that it is called a series magnetic circuit. Now we will refer the diagram so that you are able to understand clearly. So this is one magnetic material. The width is more. This is another magnetic material. This magnetic length is L1. See the width is higher, and this is a different magnetic material. This is one type of magnetic material. This is another magnetic material with the length L2. See the width, it is lesser than this. The length is L2. On other side we have L3. This is third type of magnetic material with the length L3. The thickness is very less. So in between we have air gap also available. So this is one magnetic material with the length L1. This is another magnetic material with the length L2. This is third magnetic material with L3 along with air gap is available. When the coil is excited, the flux is produced. The flux follows the single path flowing through all three different magnetic material as well as the air gap. The flux is not diverted. The single flux is flowing through all three material as well as the air gap. So that it is called a series magnetic circuit. The same flux is available across through the all three magnetic material as well as the air gap. Now we will go for the further analysis. So L1, L2, L3 is the length of the various magnetic material. A1, A2, A3 is the area of cross section of various magnetic material. Lg is the length of the air gap. Ag is the area of the air gap. So we have three different magnetic material along with the air gap. Now we will go for this further analysis. Each part of the circuit will offer reluctance to the magnetic flux. So because of different relative permeability, each part will give the reluctance to the flux. That is the different value. The reluctance value will be different due to the different magnetic material. So the amount of reluctance depends upon the dimension and relative permeability of the part. The reluctance is given to the flux, but the reluctance will be depends upon the material dimension as well as the permeability of the part, because three different material available. Since the different part of the circuit are in series, so the total reluctance is equal to the sum of reluctance of the individual part. So because of seriously connected, we will take this total flux, total reluctance equal to sum of the reluctance of 3 magnetic material as well as the air gap. So S equal to S1, S2, S3, S1 plus S2 plus S3 plus SS. Reluctance of the 3 magnetic material and air gap, sum of these 4, because it is connected in series. So we already discussed the reluctance. S can be written as L divided by mu naught mu R1 into A1. So general formula is available. Like a resistivity, here we have the reluctance. L1 divided by mu naught mu R1 into A1. This is for first magnetic material. L2 divided by mu naught mu R2 into A2 for second magnetic material. L3 divided by mu naught mu R3 into A3, third magnetic material. Then the air gap, Lg divided by mu naught mu R Ag into Ag, mu Rg and Ag. So this is the reluctance. The formula is written. So the total MMF is nothing but flux into reluctance. That is reluctance equal to MMF by flux. So MMF equal to flux into reluctance. The flux is same flux exists for all the cases. So pi into S1 plus pi into S2 plus pi into S3 plus pi into Sg. The single flux is exists. So we can take pi outside. So S1 plus S2 plus S3 plus Sg. Now we'll substitute this value S1, S2, S3 can be substituted from here. So that we got pi into L1 divided by mu naught mu R1 into A1 plus L2 divided by mu naught mu R2 into A2 plus L3 divided by mu naught mu R3 into A3 plus this air gap. Now we'll go for the further analysis. Now we'll rewrite this L1 divided by mu naught mu R1 into pi by A1. The above equation is rearranged. The length and permeability is written one side and pi and A is written another term. So what is this pi by A? Pi by A is nothing but magnetic flux density. Pi by A, flux per unit area is flux density. So that this pi by A1 can be replaced by B1. Similarly this B2, B3 and BG. Again it is rearranged. B divided by mu naught mu R1 into L1. These two are rearranged. So what is that B divided by mu naught mu R1? We know that B equal to mu H. From that B by mu equal to H. So this B by mu can be replaced by magnetic field intensity. Right? That is H equal to B divided by mu naught mu R. So this term can be replaced by magnetic flux, magnetic field intensity. So what will happen? This is the H1, this is H2, H3 and Hg. So that H1 into L1 plus H2 into L2, H3 into L3 plus Hg into Lg. Right? This is 3, not Hg, this is H3. So now we got the total MMF for a series circuit. What is that? The total MMF is nothing but sum of individual terms because it is connected in series. So that all are added together. Now we'll go to the parallel magnetic circuit. Parallel magnetic circuit, if the flux has more than one path, then it is known as a parallel magnetic circuit. The flux is diverted, then it is called a parallel magnetic circuit. In parallel magnetic circuit, the total flux exists in a common section of the magnetic circuit which contains the exciting coil. The common circuit having the exciting coil, in that the common flux, the total flux will be available. After that it is divided into two or more paths, follows the different path and recombine again at the another end of the common section. So at the common section exciting coil will be there, the total flux will be available. Thereafter the flux is divided into two different paths, again at another end it will be recombined. Now we'll refer the diagram. So in this diagram the exciting coil is available at the center limb. This side and another side, another two parts are available. The coil available at the center limb. The current I is flowing through the coil. Due to rate of change of current, the flux is produced. So this is the common section having the exciting coil. The total flux is available in this part, that is AD. It is named as AD. The other name is A, B, C, D, E and F. All the parts are named as. So in this the part AD, we have the common part, exciting coil is available, the total flux is available also in this section. So at this point the flux is diverted. This side the flux will be pi 1, this side the flux will be pi 2. So A, B, C, D, A having the flux pi 1, A, E, F, D having the flux pi 2. So at the center limb the total flux is available. At this point the flux is diverted into pi 1 and pi 2. So that is given here. The total flux, pi is the total flux in the circuit. Pi 1 flux in the path ABCDA, this ABCDA. Pi 2 is the flux in the AEFDA, AEFDA, pi 2. So the total flux pi is nothing but pi 1 plus pi 2. Then what about the reluctance? Reluctance S1. S1 is the reluctance in the path ABCDA, first part. S2 is the reluctance in the second part, AEFDA, this one. Then S is the reluctance in the AD, common part, central limb is the AD. So these are all connected in parallel. The path ABCDA and AFEDA are in parallel. In a parallel circuit, the MMF required for the whole parallel circuit is equal to the MMF required for any one of the parallel path, because both are connected in parallel. For the total magnetic, the total MMF is nothing but MMF required for any one of the parallel path. Any one of the parallel path we can consider. That is total MMF equal to MMF for the path AD. So this is a common part, plus either ABCDA or AFEDA. So it's nothing but common part plus any one of the parallel path. So that we can write pi into S. Pi into S is the total flux, common part. Pi 1 S1 means first part, ABCDA. Otherwise we can write pi into S into second part, AEFA, that is pi 2 into S2. So the parallel circuit means we need to consider any one path alone is enough. So that pi S plus pi 1 S1 considering the first part, pi S plus pi 2 into S2 considering the second part. Either this one, this equation or this equation can be used for the total MMF. So in this video we analyze the simple magnetic circuit, series magnetic circuit and parallel magnetic circuit. Thank you. Welcome viewers. In this video we will see the electromagnetic induction and its law. First we will see the Faraday's law of electromagnetic induction. The Faraday discovered that the EMF is produced in the electromagnetic induction, that is widely used in the commercial generation of power. So based on the Faraday's law, whenever conductor cuts the magnetic flux or whenever magnetic flux linkage with the conductor changes, an EMF is induced in the circuit, in the conductor. So there is a magnetic flux, there is a rate of change of magnetic flux. If there is any rate of change of magnetic flux, then the EMF will be induced. That is the Faraday discovered the EMF induced based on the Faraday's law. Also the magnitude of induced EMF depends upon the rate of change of flux linkage. So that is the expression given by the Faraday's law. So the expression for induced EMF is E equal to N d pi by dt. So this is the statement given by Faraday's law. Rate of change of flux will induce the EMF. This N is nothing but number of turns available in the coil. So E is the induced EMF, N is number of turns of the coil, d pi by dt is nothing but rate of change of flux. E equal to N d pi by dt, that is the equation from the Faraday's law. Now we'll go to the Lenz's law. The direction of induced EMF is given by the Lenz's law. Faraday's law gives the expression n d pi by dt. The direction is given by the Lenz's law. According to this law, the induced EMF will be acting in such a way as oppose the very cause producing it. There is a opposition between the induced EMF and rate of change of applied voltage. So that is a statement given by the Lenz's law. Cause producing means the applied voltage. So there are both are oppose each other. So that E equal to minus n d pi by dt. So this direction is given by the Lenz's law. It is clearly given. The EMF will acting in such a way oppose the very cause producing it. It will oppose the rate of change of flux. So that E equal to minus n d pi by dt. Right? The direction is given by the Lenz's law. Now we'll go to the Fleming's rules. There are two rules available, Fleming left hand rule and Fleming right hand rule. First we will see the Fleming left hand rule. What is Fleming left hand rule? It is what is given. In the left hand we have to stretch the forefinger, middle finger and thumb finger which is perpendicular to each other. So that this forefinger will indicate the magnetic field. This middle finger will indicate the current. So the motion of conductor is indicated by the thumb. So this is the Fleming's left hand rule, the statement given. In a left hand, if you stretch the fingers in such a way that forefinger, middle finger and thumb are perpendicular to each other, forefinger will indicate the magnetic field, middle finger will indicate the current, thumb will indicate the motion of conductor. Now we'll see the statement. According to this rule, if the middle finger, forefinger and thumb of left hand are at right angle to one another, we need to stretch the three fingers such a way that it is right angle to one another. In such cases, if middle finger and forefinger will represent direction of current and magnetic field respectively. Middle finger and forefinger will represent, middle finger represents the direction of current, forefinger will represent the magnetic field. So that the thumb will indicate the direction of force acting on the conductor. The thumb will give the direction of force acting on the conductor. So this is used in a DC motors. So we are able to identify the three quantities, that is direction of current, magnetic field, direction of force on a conductor. So in a DC motor, when a current is flowing, the flux is produced. Due to the flux, rate of change of flux, the conductor is start rotating, right? So the current flows, magnetic field is created, so the motor will start rotating. So these three things are given by this Fleming left hand rule, that all these three are perpendicular to each other. So that is the concept given by the Fleming's left hand rule, right? When the current flows, magnetic field is created due to rate of change of flux, the conductor starts, the armature start rotating. These three are represented by the Fleming left hand rule. Now we'll go to the Fleming right hand rule. So the Fleming right hand rule is used to determine the direction of induced EMF in a conductor. The previous case is the direction of motion, force acting on a conductor. Now we can see the induced EMF in a conductor, right? So in a right hand, if you stretch the thumb, forefinger and middle finger which is perpendicular to each other, the thumb will give the motion of conductor, forefinger will give the magnetic field and middle finger will give the induced EMF. These three fingers are indicated these three parameters, which are all are perpendicular to each other. Now we'll see the statement. According to this law, if middle finger, forefinger and thumb of the right hand are at a right angle to one another. In a right hand, we need to keep these 3 fingers at right angle to each other, middle finger, forefinger and thumb, in such a way that the forefinger and thumb represents the direction of magnetic field and direction of motion, so that this middle finger will indicate the induced EMF in the direction of induced EMF. So it is used in the DC generators. The DC generator means EMF will be induced. So while applying the magnetic field and when the conductor rotates, the EMF is induced, so that the direction of magnetic field, the direction of rotation is indicated by forefinger and thumb. The induced EMF is indicated by middle finger. So in a generator, what we are doing, we are rotating the conductor so that magnetic field will cuts the conductor. Accordingly, the EMF will be induced. These 3 parameters are explained by the Fleming's right hand rule, right? So that is used in the DC generators. So in this video, we discuss about the electromagnetic induction and its law. The first we discuss the Faraday's law of electromagnetic induction, then Lenz's law. Lenz's law will give the direction. Then Fleming's left hand rule, that is applicable for DC motors. Fleming's right hand rule, that is applicable for DC generators. Thank you. Welcome viewers. In this video, we will see the induced EMF. An EMF is induced in a coil or conductor whenever there is a change in flux linkage. That is based on the Faraday's law. Whenever there is a flux linkage, EMF is induced in the coil or conductor. So this change in flux can be brought into the following 2 different ways. The change in flux can be done in a 2 different ways. First we will see the first one. In the first case, the conductor is moved in a stationary magnetic field. We have 2 terms. One is magnetic field, another one conductor. If the conductor is moving in a static magnetic field such a way that there is a magnitude change in the flux linkage, this kind of induced EMF is known as dynamically induced EMF, because the conductor is moving. The conductor is moving and the magnetic field is stationary. Due to movement of this conductor, there is a flux linkage, so that EMF is induced. Because of conductor movement, we termed as dynamically induced EMF. So that is applicable in a generators. The generator, the conductor is a moving part. In the second case, the conductor is stationary, but the magnetic field is moving or changing. Magnetic field flux linkage is moving from one coil to another coil, but the conductor remains stationary. So this kind of induced EMF is known as statically induced EMF, because conductor is stationary. So it is applicable in the transformer. Transformer is a static device, not a rotating device. The conductor also stationary, only the magnetic flux is moving from primary coil to secondary coil. There is a flux linkage between primary coil and secondary coil. So due to the stationary conductor, it is termed as a statically induced EMF. Now we will go for the expression of the first case and second case. First we will consider the dynamically induced EMF. So we already discussed, when a conductor is moved in a stationary magnetic field, so that magnetic flux linkage with its changes in magnitude as the conductor is subjected to a changing magnetic, therefore the EMF is induced. The conductor is moving, so due to that magnetic flux linkage will changes, so that the EMF is induced. The induced EMF in such a way that is a dynamically induced as a DC generator or motor. It is called because EMF is induced in a conductor when it is moving. Due to the movement of conductor, we are saying that it is a induced EMF. Now we will refer the diagram. So in this diagram, this is the magnetic field. This line represents the uniform magnetic field with the magnetic flux density of B. This uniform. Here one conductor is available. Now initially it is stationary. This V is nothing but velocity. So due to flux linkage, it will move at an angle. So this is the second position, movement. This is the magnetic field of line conductor. Conductor is moving at an particular angle. So this is a vertical component V sin theta. This is horizontal component V cos theta. So this is the angle. It is in a stable condition. It is at a rotating condition. So when this conductor placed in the magnetic field, due to change of this magnetic flux linkage, the conductor will start rotate. This is stationary, this one rotating position. It is rotating at an angle of theta. Now we will see what is the expression for induced EMF. So here we consider a conductor with the length L meters moving in a velocity of V meter per second at right angle to the uniformly stationary magnetic field of flux density B Weber per meter square. So we consider one conductor with the length is L. The velocity is V meter per second, that is at a right angle to the stationary magnetic field with a flux density B Weber per meter square. Let the conductor moves through a small distance dx in a time dt seconds. We assume that when due to flux linkage the conductor is moving. Now we assume that the conductor moved by the small distance is dx. The time is dt. Now we will go to the derivation. So the area swept by the conductor, the area covered by the conductor is L into dx, length of the conductor into distance covered by the conductor. So A equal to L into dx meter square. Area covered by the conductor is nothing but length of the conductor and distance moved by the conductor, L into dx. So magnetic flux cut by the conductor is d pi is magnetic flux density into area covered, area swept. This B equal to pi by A, so pi equal to B into A. So d pi equal to B into this area covered is L dx. So from this, right? So the magnetic flux density is B, this area swept is L dx. So BL dx d pi. So according to Faraday's law, due to rate of change of flux, the EMF is induced. So E equal to N d pi by dt. That is the expression given by the Faraday's law. Now we will substitute the pi from the above equation. So N d pi by dt, pi is BL dx. So by simplification we got BL dx by dt. This BL is constant, bx by dt. The N is taken as 1. Number of turns is only 1. So the dx by dt, distance divided by time is nothing but velocity. So E equal to BL into V. Magnetic field intensity, length of the coil and velocity. So dx by dt is nothing but velocity. Now we will go for further simplification. So this equation E equal to BLV is giving the dynamically induced EMF when the conductor moves right angle to the magnetic field. Suppose if the conductor move at an angle of theta, is represented in the second diagram, to a magnetic field, then the EMF induced due to only the perpendicular component of the velocity is given by E equal to BLV sin theta. We need to consider only perpendicular component. Horizontal component no need to consider, only perpendicular component is considered, so that E equal to BLV sin theta. So the induced EMF, dynamically induced EMF is nothing but E equal to BLV sin theta. Now we got the expression for induced EMF. Now we will go to the second case, statically induced EMF. In the statically induced EMF, again there are two types available, self-induced and mutually induced. Self-induced means only one coil. Mutually induced means there are mutual inductance between two coils are available. First we will consider the self-induced EMF. So consider this coil. One iron core is available over which the coil is winded, having only one coil. So that is called a self-induced. So when the supply is given and the voltage is given, the current will start flowing through the coil. Due to rate of change of current, EMF is induced in the coil. Flux is produced. Flux is produced in the coil. So this line, the red color dotted lines is nothing but a flux produced by the coil. So this is the inductor. This coil is termed as inductor. Due to rate of change of flux, EMF is induced in the coil. So we have iron core over which coil is winded. When the supply is given, the current starts flows. Due to rate of change of this current, flux is produced in the coil, that is indicated by the red color dotted lines. Due to rate of change of flux, EMF is induced in the coil. So this is nothing but self-induced EMF, because we have only one coil, the EMF due to only the self-inductance. So that it is called a self-induced EMF. Now we will see the description. When an EMF is induced in a coil due to the change of its own flux, due to its own magnetic flux, only one coil, the rate of change of flux due to its own coil, then it is known as a self-induced EMF. We will see the another description. So when a current flowing in a coil, magnetic field is produced. By this, current flows through the coil. If the current in the coil changes, the magnetic field linkage also changes. So due to the Faraday's law of electromagnetic induction, the change in flux will induce the EMF in the coil. Now we will go for the derivation. So due to its own flux linkage, the induced EMF is known as a self-induced EMF. So the self-induced EMF, we can get it from the, first we will start with the inductance. L equal to N pi by I. It's a general formula for inductance. Cross multiply this so that Li equal to N into pi. Now differentiate on both the side so that L into di by dt. So here the current is changing. N is constant. So d pi by dt. So L di by dt equal to N d pi by dt. We start from the inductor expression, cross multiplied and differentiated on both the side with respect to time. So but from the Faraday's law, E equal to minus N d pi by dt. We know that E equal to minus N d pi by dt. So other case, N d pi by dt can be written as minus E. So we can replace this term N d pi by dt with the term minus E, because based on the Lenz's law, we have negative sign. The opposing, Lenz's law giving the clear cut expression that it is opposing, so that we are getting negative sign. So this equation become L di by dt equal to minus E. Based on this, N d pi by dt is replaced by minus E. So that can be written as E equal to minus L di by dt. So this is nothing but self-induced EMF. E equal to minus L di by dt is the expression for self-induced EMF. Self-induced EMF means having only one coil, EMF due to its own flux linkage. Now we will go to the mutually induced EMF. When an EMF is induced in a coil due to changing magnetic flux of neighboring coil, another coil, is known as mutually induced EMF. Mutually means there are two coils available. The EMF induced in the first one coil is due to magnetic flux linkage in the second coil, another coil, neighboring coil. In that case, it is called a mutually induced EMF. Now we will see the diagram. Now consider the two coils. In previous self-induced EMF, we have only one coil. Here mutually induced, we have two coils are available. So this is iron core over which the coils are winded. Here also another coil is winded. In the first coil, the supply is given, so that the current will flowing through the coil. Due to rate of change of current, flux is produced in the first coil. That flux with link with the second coil, because both are placed nearer. So this is nothing but a mutual flux between coil 1 and coil 2. See here the flux is moving from one coil to another coil. The coil is stationary. So we have two coils are available. The first coil supply is given, current is flowing. Due to rate of change of current, flux is produced. That flux linked with the second coil, that is nothing but pi m. Due to flux linkage in the second coil, EMF will be induced in the second coil. This This EMF is due to rate of change of flux in the second coil and current through the first coil. So that it is called a mutual flux and mutually induced EMF. Now we will see the description. Consider two coils 1 and 2 placed adjacent to each other. The fraction of magnetic flux produced by coil 1 links with the coil 2. That is the mutual flux. The magnetic flux which is common to both coil 1 and 2 is called a mutual flux, pi m. So, it is indicated in the diagram. Now, if the current in the coil 1 changes, mutual flux also changes, thus EMF is induced in the both the coil. Right? The flux produced in the coil 1 linked with the second coil also. So, there is any change in the current will change in the flux, due to that the EMF will be induced. The EMF induced in coil 2 is known as mutually induced EMF, since it is induced due to change in flux which is produced by coil 1. The EMF produced in coil 1 is due to the flux linkage in the coil 1. So that it is called a mutually induced EMF. So we can see the derivation for the mutually induced EMF. We start from mutual inductance. M equal to N2 pi 1 by I1. First we consider the second coil. N2 pi 1 by I1. So cross multiply this. So that is M I1 equal to N2 pi 1. M I2. Now we will go for the further simplification. Now differentiate the above expression with respect to time. So that M di1 by dt equal to N2 d pi 1 by dt. This M is constant, so it is I is differentiated, here pi is differentiated. But we know that from the Faraday's law, E equal to minus N2 d pi 1 by dt, rate of change of flux. So that can be written as N2 d pi 1 by dt equal to minus E. So we can replace this term N2 d pi 1 with a minus E. So this minus is nothing but based on the Lenz's law. So that M di1 by dt, this one equal to, this term is replaced as minus E. So that can be written as E equal to minus M di1 by dt. So this is nothing but mutually induced EMF, minus M di1 by dt, the expression for mutually induced EMF. Is a second coil. Suppose if it is induced in the first coil, the second coil is energized and EMF is induced in the first coil, the same thing can be written as E equal to minus M di2 by dt. Here we have di1, EMF induced in the second coil, current flow in the first coil. Here EMF induced in this first coil, the current flows in the second coil. So both are induced EMF. This one refers the second coil, this one refers the first coil. So in this video we discuss about the self-induced EMF and mutually induced EMF. We got the expression for both self-induced and mutually induced EMF. Thank you. Welcome viewers. In this video we will see the analogy between the magnetic circuit and electric circuit. So we have this magnetic circuit, the details available. Here the electric circuit details are available. First we will see the closed path for the magnetic flux forms a magnetic circuit. Magnetic circuit is formed by the magnetic flux that will form the closed path. In case of electric circuit, the electric current that form the closed loop. The closed loop for the electric circuit form an electric current. So here magnetic circuit we have flux is available to form the closed loop. Here current is available to form the closed loop. The magnetic flux does not flow in a magnetic circuit. So we assume that there is a magnetic flux is available that is flowing through the core of the core. We are assume that is a imaginary. Fluxes are imaginary. But in electric circuit, the electric currents are always flowing. There is a real flow of electric current in a electric circuit. Then the MMF, magnetomotive force, is the cause for the producing the flux. Magnetomotive force, that is the cause for producing the flux. Similarly here electromotive force, EMF, is the cause producing for the current. So the current is produced from electromotive force, flux is produced from magnetomotive force. The unit for the flux is Weber, the unit for current is ampere. So here it is clear that the flux in the magnetic circuit is equivalent to current in the electric circuit. Then the flux is given by flux equal to mmf divided by reluctance, magnetomotive force divided by the reluctance. Similarly, the current is electromotive force divided by resistance. So very similar, mmf by reluctance, here emf by resistance. The reluctance is nothing but oppose the flow of flux, that is resistance oppose the flow of current. The flow of current is opposed by the resistance in electric circuit. Similarly, here the reluctance is opposing the flow of flux. So the reluctance is given as L divided by mu naught mu r into A. Very similar to resistance is given by rho L by A. Rho is nothing but a resistivity. So here L by A is very similar. Here also L by A is available. Here rho available in the numerator. 1 divided by this mu naught or mu r available in the denominator. That is the difference. L divided by A similar for both the cases, reluctance as well as resistance. So the permeance is nothing but 1 divided by reluctance. The reciprocal of the reluctance is nothing but permeance. Similarly, the reciprocal of the resistance is the conductance. Both are reciprocal. The flux density is nothing but flux per unit area, pi by A. The flux density is nothing but flux by area. Similarly, current density is current per unit area, I divided by A. Then the magnetic field intensity, H is nothing but Ni by L, mmf divided by length. That will give the magnetic field intensity. Similarly, the electric field intensity is given by E equal to V divided by D, potential divided by distance. So the magnetic flux lines flow from north pole to south pole. Always it will flow from north pole to south pole. Similarly, the electric current flow from positive to negative terminal. Positive to negative terminal. So these are all the analogy between the electric and magnetic circuit. Thank you. Welcome viewers. In this video, we will see the magnetic leakage or leakage flux. What is meant by leakage flux? The leakage flux is nothing but the part of magnetic flux that does not follow the desired path in a magnetic circuit is called a leakage flux. The magnetic flux are following a certain path. Some fluxes are deviating from that desired path, that is nothing but a leakage flux. We will see this diagram. So the iron core is available, one air gap also available here. At one end the coils are winded. The current is flowing through this coil. Due to rate of change of current, flux is produced in the coil. That flux will follow the closed loop through the iron core. The flux is always following through the iron core. So at this point we have the air gap is available. So through the air gap also the fluxes are flowing. The fluxes flowing through this air gap is a useful flux. See this, some of the flux are deviating the desired path. It's going out, fledged. It is bulged outside. So that is called a fringing. Also here in the coil also some of the fluxes are available outside the coil. That's called a leakage flux. So this is a flux path flowing through the core of the flowing through the iron core. In that air gap the fluxes are flowing through the air gap also. That air gap fluxes are called as useful flux. The fluxes deviated is called a leakage flux. So from that we can see the description. In most of practical magnetic circuit, the path of large part of the magnetic flux is through iron part of the magnetic circuit. So normally the flux is flowing through the iron part. The rest of the part, the flux is flowing through the air. That is called air gap. Mostly it is flowing through the iron core. few of them will flowing through the air. So the magnetic flux in the air gap is called a useful flux, pi g. The flux flowing through the air gap, because it is flowing from one end to another end through the air. Since it is used for various useful purpose, that fluxes are useful. Through the air it is passing from one end to another end. That's why it is called a useful flux. At the same time, consider the magnetic circuit having an iron core with coil winded on it, having a narrow air gap. We discussed the diagram that is given. Magnetic circuit is available, iron core is there. Over the iron core, the coil is winded and air gap is available. The total magnetic flux produced by the coil does not pass through the air gap. Some of the flux only pass through the air gap. Some part of it leaks through the air gap, that is surrounding the iron core. So that is called a leakage flux. Thus we discussed that the fluxes are deviating the desired path is nothing but a leakage flux. That is given as pi leakage. Now we will go for the definition. We will take the total magnetic flux produced in the coil is pi I. Pi I is the total magnetic flux produced in the iron core. The useful flux in the air gap is nothing but pi g. That also we discussed. Through the air gap, the flux is flowing is called a useful flux, that is pi g. So that the leakage flux, pi leakage is nothing but total flux minus this leakage useful flux. The remaining flux will be the leakage flux, pi I minus pi g. So the leakage coefficient, from that we can able to identify the leakage coefficient, that is nothing but total magnetic flux divided by useful magnetic flux. What is total magnetic flux? That is pi I. The useful magnetic flux is pi g. So pi I divided by pi g will give the leakage coefficient. We can able to identify the term leakage coefficient. The value of this leakage coefficient lambda for electrical machine is usually from 1.15 to 1.25. The value is ranging from 1.15 to 1.25. So from that we can able to identify what is magnetic fringing. So we discuss the total flux, useful flux, leakage flux. So that we will see what is the fringing. When the magnetic field pass through an air gap, they tend to bulge out. Bulged out means it is not following the desired path, it will deviate. So we clearly see in the diagram. This is because the magnetic field line repel each other when they passing through the air. So some parts are deviated, bulged. So this effect is known as the magnetic fringing, right? So in this video we discuss about what is the useful flux, what is the leakage flux, and what is magnetic fringing. Thank you.